You're welcome, everyone. Trust you're all doing well and you're doing your best. This week we're looking at magnets, magnetic field, electromagnets, and other stuff. Now, the first thing I would like you to remember or to realize is that when you talk about magnet, we're talking about a substance that has two poles. Every magnet has north and south pole. Okay? You can also have permanent magnet, you can have temporary magnet. When we say permanent magnet, we are talking about a substance that has been magnetized, okay? Which could be electrical method, it could be double stroke, single stroke, as the case may be. But first of all, let's look at the magnetic field pattern. Magnetic field is a region around the magnet where when you brought another magnet into that field, force will be created. So I have here the north and south pole. The field lines in the magnet enter at the south pole and they leave at the north pole. Alright? And we can also have, if I have two magnets of like poles brought together, for example, north and north poles brought together, I'm going to have what is called repulsion. Repulsion because the field lines, they are not connecting. While you're leaving from both of them, that's not connecting them. And this normally leads to what we refer to as a neutral point. Neutral point is a region within like poles where the horizontal field line is zero. Okay? So this region is called neutral point. Now let's look at if I have two poles that are in opposite poles, north and south pole, the field lines will leave the north and enter the south pole, so which creates attraction. Okay? At the end of this class, I'm going to demonstrate these two instances to you, and I hope you watch out properly. You follow me. Now, apart from having magnetic field in a system, magnetic field when you have one magnet, you can also have magnetic field in a current carrying wire. Now, look at this one now. A current carrying wire in which current is flowing upward. This dot, we use the dot to represent when you view that wire, when current is flowing towards you. And because magnetic field is a vector quantity, we need to also remember that it must have direction. So what we use to predict direction of current carrying wire is our right hand. We call it right hand grip rule. If you assume that your thumb is direction of the current, your fingers, which you use to grip, right now I'm gripping this marker, which you use to grip, represent the field pattern. So in this case, the direction of this will be, anti-clockwise. Now, if I reverse direction of that, now you can see my thumb is going towards the board now. My fingers are rotating this way, which is clockwise. So this is going to be clockwise direction. I hope that is clear to you. So when you view the tail of a current carrying wire, the magnetic field, which is of course a circular pattern, is going to move in the direction of clockwise. But when you view the head of the current carrying wire, it will be anti-clockwise. Don't forget. Now we're going to use this knowledge now to predict or to understand how magnetic field is being developed when you have an electromagnet. I have on the board what we refer to as a solenoid. This is solenoid. What do I mean by solenoid? A solenoid is simply we have a core. A core, you can do this at home. You have a bobbitter tin or all these branches thing, and you have copper wire wounded around it. So this material is called core. Okay? The wires that was wounded is called coil. So you have coil around the core. Now when you now have the ends of such connected to a key or switch, a battery power source, remember that your battery, the long pole is the positive, current will normally leave from the positive, and once the current is going, the blue color is what, that's my current flows, go to the bar like that. So now, we said the head of current is represented by the dot, and hex is the tail. Now, if you observe closely, while this current is going away, it goes to the back of this core. So once it's going to the back, you can only observe the tail. So you observe tail at this point, or this point. That's why we have hex, written there. And when they are coming from the back, once it goes to the back, it's coming from back to go up, Like for example, something goes this way, it's coming from the back up. That's what you see here. So when you're coming out, you see the head. These are heads. Now, if you transfer the knowledge from this place to here, you see that for those heads, the direction of magnetic field is anti-clockwise. And because we are focusing on the internal part of our core, so while this one is anti-clockwise, this one is clockwise, you see that those places within the core, within this material, they are facing this place. So once if you have more field lines, what will happen is that the effect of those field lines will create a bigger magnetic field, which will make this material, this electromagnet, to have a larger magnetic field line, which is similar to our parent magnet here, and that will make this material to have a north pole and south pole. If you look at it closely, while this is coming out, this is going this way, so it's entering from this place south. This one is also coming out, entering here south. So this is south and this is north pole, which is replica of what I have in south pole. So this field line makes this to behave like a magnet, temporary magnet, so long as current is flowing. All right. So this is what we call an electromagnet, meaning that we use electricity to produce magnet. Okay, very important. All right. So you need to also remember that we have methods of making magnets. We have something we call single stroke method. Single stroke means, for example, I have a magnet with me. Let's say this material is to be made a magnet. It must be a metal. What I do is single stroke is you strike it the same direction. This is single stroke. Okay, once you do this for 100 times, you see that this material will behave like a magnet. Of course, not very strong. Another method is you can also have double stroke. Double stroke is you have two magnets and you move them, in this direction for so long, this material will behave like a magnet. Another method is when you have, that one we call that electrical method. That's when you have a circuit. In this electrical method, you must have a power source, which must be DC source, and your circuit must be in the north and south direction. Okay? Once that is done, they are a magnet. Quickly, we need to also know that we can destroy or demagnetize. Many methods, you can have electrical method, you can also have demagnetize by hammering. Okay, you hammer. Once you allow hammer to strike a magnet, you are going to destroy magnetic field pattern. Or you place your magnet on hot plate, by heating it with fire. Okay, you can also do that. So just follow me as I demonstrate to you what I promised earlier on about magnetic field and also attraction and repulsion. Thank you. We see that now. Okay. I have with me two magnets, and as you can see, this is south-south pole. We also have the north pole. I have north and south. Let's see what will happen between them. I'm not going to, I will just put them and you see how they behave. Don't forget north and south pole. I'm sure you can see that the two poles, they are opposite poles, they attract. Let's try the like poles. North pole, let's see how they will behave. If you observe, good, you see the south pole actually twisted, but let's see what will happen if we make the two poles. I'm sure you can see that it's the opposite that is attracting, but the similar pole seems, you can see I'm not the one pushing it, it's moving back, meaning that it's repelling. Okay, they are repelling. So thank you. I think that's okay. So we'll see the next one very soon. Thank you so much. Good. As we were saying, now we want to see magnetic field patterns due to magnets. I have iron filing on white paper here, and I have these two magnets. You can see this is south pole, and for this is my north pole. So let's see what will happen to one first. Let's see the magnetic field around a bar magnet. Now, if you observe, you see that a pattern is forming already. I'm sure if you observe closely, you have a pattern that shows that there's something around the magnet, and that is called the magnetic field. Okay, now let's introduce the second magnet to see what happens when we have like poles. I have north pole here and south pole, so we place our field line, the iron filings back. Let's see, don't forget we have north and south pole there. If you observe closely, you see that this is end of one magnet, this is second one. I have iron filing, meaning that two of them are attracting. They are actually attracting because the two field lines, they interact. Okay, so this is opposite pole for attraction. Let's change one of the poles. Now I've changed the second one, meaning that I have like poles now, south and south pole. Let's see the behavior. So I spread my iron filing around them. Now what you will observe, ladies and gentlemen, is that the field lines seems not to be much between the poles, meaning that there is no, iron filing is something between the, so there is no field lines here. That's why we don't have iron filings in between here again. You know, when I was talking the other time, I talked about neutral point. So the point where the southern field is 0 is called neutral point, and that will happen between like poles, and that's what you can see here. Okay, I hope this will help you. Thank you very much, and I see you another time. Have a nice day.